Okay, so to see where our traditional model, the OLS or ordinary least squares, falls short when we have a binary outcome, let's set up an example here. So in our example, we're looking at the different risk factors for heart disease, and so a main predictor of that is going to be age, right? And we have an identification code for each patient. Now, the outcome that we're interested in is going to be the presence or absence, so absence is 0, presence is 1, of significant coronary heart disease, or as I'm going to call it from now on, CHD. Now, we have 100 subjects, and our goal is going to be to explore the relationship between age and presence of CHD. Now, let's just take a look at the data. So here we're loading the data into R, and we're just looking at the header, so the first 6 observations in the data set. And here I'm just plotting the scatter plot of age as well as outcome here. So again, remember, our outcome can only be 0 or 1. And so here you can see that the scatter plot is going to look a little funky in comparison to a scatter plot that we're normally used to looking at that has values that can fall between 0 and 1. Now, if we are going to apply just the normal regression model, right? Again, here our outcome y is going to be 0 or 1, whether or not a patient has CHD, and our main predictor is going to be age. We're still going to estimate an intercept as well as a beta for the relationship between age and CHD. Here I'm just running, again, that normal OLS model with our outcome CHD and our main predictor age. So what we get from the fitted model from R is a an estimated coefficient of the relationship between age and CHD is around 0.02, and the intercept, so when an individual is 0 age, their predicted CHD is going to be negative 0.4. Now we can go ahead and not only interpret the estimated coefficients from that OLS model, but we're also going to check to make sure the assumptions of the linear regression hold. So here again, remember, we can see in the first top left the fitted values plotted with the standardized residuals. We can also see in the normal QQ plot deviations from normality for different theoretical quantiles, so different values of x. And at least in this instance, we would say that at least in the first instance, our assumptions are quite violated, right? So there doesn't seem to be a constant, the regression line between the fitted values and the residuals is not straight at 0. And moreover, we can see that there are differing values from normality at the extreme ends of age. This is going to lead to a number of problems. First of which is the fact that we're going to get predictions for observations that are going to be outside of 1 to 0. So like I said, if an individual is of age 1, right, the predicted CHD is going to be negative 0.1, and that's just not possible, right, because you either have the condition or you don't have the condition. So basically what's happening here is we're getting a conditional mean given x that falls outside the possibility of potential values for y. Now, for someone who happens to be 100 years old, right, we can calculate their CHD and we find that it's 1.46. Again, that is not a value that is possible. The second assumption that's going to be violated is that our assumption of the normality of those errors is not reasonable, just like I stated that we'd find in that figure 2. So the distributions of y's are not going to be the same, right? They're not going to have the same variability across different values of x. And so that means that y at different values of x is going to have a non-linear relationship with y. And that is very problematic, right? Because that's a central assumption of OLS.